Today we're going to talk about the periodic table. Some of the features, how it's set up, what information we can get off of it, and how we can use it as a tool to predicting chemical reactions. Um, it's very, very important that you understand this stuff. So um, there's going to be notes, so I would highly suggest that you pause the video at certain times to write these notes down, because you are going to be responsible for all this information I'm giving you today. I would print out a blank periodic table so you can write some stuff down that is super, super important that we're going to use throughout the entire rest of the year. So I can't emphasize how important this stuff is today. All right, so let's start talking about the table. One of the features that you might notice about the table is this thick, bold zigzag line that goes down the right side of the periodic table. This is the dividing line between metals and nonmetals. Most elements are metals. So anything to the left side over here of this zigzag line are metals. Even this block down here. Okay, we're going to learn in a few minutes that the periodic table is separated into blocks. All right, and on the other side of this zigzag line on the right side, we have what we call the nonmetals. Now, things that are touching the zigzag line on at least two sides are called metalloids. So we have metals on this side, nonmetals on this side, and things that are on the line, they're called metalloids. Now, there is an exception. So for example, boron, silicon, germanium, antimony, arsenic, and I'll give you these notes in a minute. These are all metalloids because they're touching the line on at least two sides. Aluminum, however, is not a metalloid. I'll repeat that again. Aluminum is not a metalloid, even though it is touching on both sides. Okay? That's something important to know because aluminum is really categorized like a metal, so it's kind of the exception to the rule. Okay? The periodic table, we have columns that go up and down. They're called families or groups. And if you notice on your periodic table, there are 18 of them. 1, 2, all the way up to 18. Now, this group down here doesn't have numbers. All right, I will tell you why in a little while, but it's numberless. We call this group down here the F block. And it really should get inserted right between these two blocks right here, okay? Because group 1 and 2 is another block called the S block, and this little chunk right here in the middle is called the D block. And again, I'll give you those notes in a second. And one of the reasons why I like to use this periodic table, it kind of reminds you that this should be inserted between what we call group 1 and 2, the S block, and group 3 to 12, the D block. But if you did that, the table wouldn't fit into a normal sized piece of paper. It would be too long, and all the information would be bunched up, and you couldn't see the numbers, and it would be very, very difficult tool to use. So they pulled this block out, this lanthanide and actinide series, for the sake of room. Okay. So again, to reiterate, most everything on the periodic table are metals. Everything to the left side of the zigzag line are metals. Even the lanthanide and actinide series down here at the bottom of the table, they're all metals. On the right hand side you have your nonmetals, and on the zigzag line you have metalloids, which are considered what we call semiconductors, with the exception of aluminum. Okay, so we'll go back to the periodic table in a minute or so. I was talking about blocks. Okay, the periodic table is divided into 4 blocks, the S, P, D, and F blocks. The S block are these first two columns or families or groups. It's hard to see on here, but this is group 1 to 2. The D block goes from 3 to 12, and I'll give you those notes in a minute, so you don't have to write anything down just yet. The P block, group 13 to 18. Okay, and that's colored in it's kind of green color here. And finally, we have the F block down here, and that kind of gets separated out of the periodic table. Okay. There is a little bit of an exception, though, is that helium over here should be a part of the S block. And the reason why they put it over here, because it has we call a complete outer shell of electrons, and it is a part of this last column, which is called the noble gases. So even though helium is a part of the S block, they put it over here. Okay, so that the periodic table is not perfect, but it's pretty good. There are 7 horizontal rows, which we call periods. So periods go across, groups or families or columns are up and down. Okay, and you can see it here. It goes 1 to 7. All right, so right now there are 7. Maybe, someday there will be an 8th group. All right. So you need to know where the blocks are and what elements fall into those blocks. So, like I said before, the S block are groups 1 and 2. The P blocks consist of group 13 to 18. So 13, 14, 15, 16, 17, and 18 are the P block again, but helium is a part of the S block. Any elements in the S and P blocks are called main group elements. The D block consists of all these groups right here, essentially 3 to 12. Any element in the D block is called a transition element, or sometimes they are called transition metals, since they are all metals. The reason why they're called transition is because they have the ability to change charge. Now we're going to find out that all metals, most of the time in normal chemistry, usually have a positive charge, making them a cation. Okay? And again, since they can change their charge, we have to indicate that change with Roman numerals. Those Roman numerals are usually in parentheses. So for example, if you saw a Roman numeral 2 after iron, it would have a positive 2 charge. If you saw an IV after the word iron, okay, or the element iron, it would have a positive 4 charge. Now remember, when you write charge, the number comes first, then the sign. These are the Roman numerals right here. The most positive cation you can have would be a positive 8. So you need to know the Roman numerals 1 to 8. Now, some people know Roman numerals well, some people don't. So just in case, I put them down here. Again, I is a positive 1. II is 2 plus. 3 I's is 3 plus. IV is 4 plus. V is 5 plus. V is 6 plus. VII is 7 plus. And VIII is 8 plus. If I see people making mistakes, it's usually they mess up, or they think that is 6 or that is 4. They kind of, for some reason, they kind of cross the plus 4 and plus 6 Roman numerals. The F block consists of the lanthanide and actinide series, which I talked about. They're at the bottom of the table. All right, so any element in the F block are called inner transition elements, or sometimes inner transition metals. So if you need to pause the video to finish writing these notes out, please do so. So coming over here to the next page, Again, germanium, indium, antimony, thallium, lead, and bismuth. Those are called post-transition elements or post-transition metals. They also need Roman numerals, just like the transition metals do. Now, some characteristics. Metals have luster. That means they're shiny. Metals are malleable and ductile. We went over that at the beginning of the year. Another important characteristic of a metal, they can conduct heat and electricity. So the electricity coming through your household wires are copper. Copper does an outstanding job of conducting electricity. Metals will form cations, positive ions. Okay, so metals will be positive. Not saying that they can't be positive. Sometimes they can be negative, but it's very, very rare, and that's kind of exotic chemistry that kind of falls out of the field of the stuff we're going to do. So for us, metals are always going to be positive. Non-metals are dull, not shiny. They're brittle. That means they break apart and they shatter into little tiny pieces. They do not conduct heat or electricity. Matter of fact, we use non-metals or elements and compounds of non-metals to coat your electrical wires, so when you plug something into the wall, you don't get shocked. They form anions. That means negatively charged ions. So again, if you need to pause the video to copy all this stuff, please do so. And going on to the last page before we actually go back to the periodic table and start talking about it. Elements on the zigzag line, on the staircase line, are called metalloids. So your metalloids are boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. We won't talk too much about polonium because polonium is a radioactive element, so we don't really do normal chemistry with radioactive elements. These elements look metallic. They do not conduct electricity as well as metals. They are called semiconductors. So your computer chips are made of silicon or semiconductors. So your chip in your phone, your chip in the computer, and your Chromebook, they're all using the fact that silicon conducts metal slightly. And again, if you can conduct metal slightly, and you can turn that current on and off, you can talk binary, and that's how your computer system essentially gets programmed. Anyway, so some groups have names. Well, actually, they all do, but these are the only four you're going to be held responsible for. Group number 1 is called the alkali metals. Group number 2 called the alkaline earth metals, and group 17 are called the halogens. And finally, we get noble gases in group 18. Okay, so that's some basic background information on the periodic table. So let's go and talk about the periodic table itself. All right, so the really important thing about the periodic table is that you understand and you're able to look at it and know where charges are. All right, so instead of sitting and memorizing a whole bunch of charges, okay, you just look at the periodic table and use it as a tool. Say, well, okay, well, what's the charge of calcium? So if I know what calcium is, I essentially know the charge. All right, especially of those of the main group. All right, so again, we said the metals are on the left-hand side, the non-metals are on the right. So let's talk about the group 1 or the alkali metals. Now there is also, again, an exception to this. Okay, hydrogen over here is considered to be a non-metal, even though it's on the metal side. Now the reason being is that hydrogen, like these metals, these alkali metals that we talked about, will form a 1+ charge. Now hydrogen can form a 1 minus charge, but for the most part, hydrogen tends to be a positive 1 and has kind of metallic characteristics, even though hydrogen is a gas, okay, and a non-metal. So it's not a part of the alkali metals. I want to make that perfectly clear. Hydrogen is not a part of the alkali metals, but they put it over here because it gets a positive 1 charge, and it's, matter of fact, the only non-metal that will get a positive charge. Okay, all the rest of the non-metals will become negative. So I don't have to memorize the charges for all these 7 elements. So if I understand that where cesium is, or cesium, whatever you want to call it, I understand that that is a positive 1 charge. Or sodium. Sodium is a positive 1 charge based upon where it is. Now that charge is set. They will always be positive 1. The next column over, group 2, the alkaline earth metals. Well, everything in that group will always have a positive 2 charge. Again, which is very helpful, so I don't have to memorize 6 elements. I just know where they are. We're going to jump across the table to the nonmetals, the noble gases. Well, noble gases don't get a charge. Their charges are 0. Now, I know you might say, well, you know, helium is going back to nuclear chemistry, helium has a positive 2 charge, but that's not under normal conditions. That's under nuclear decay. So for the most part, any element over here, okay, in this group, for normal chemistry, do not get charges, never. We're going to go over here now to group 17, which is the halogen family. So everything in this column will get a -1 charge. So fluorine, chlorine, bromine, iodine, and astatine will always have a -1 charge. Okay? Go into column 16, which is the oxygen group. Everything will have a -2 charge up to this line. Okay? So oxygen, sulfur, selenium, and tellurium, again, all being in the same family, will get a -2 charge. Now, the reason why polonium doesn't get a -2 charge is because polonium's on the side, it's a metalloid, and it's on the side of the metals. So again, metalloids that are on the metal side tend to have more metallic characteristics, where metalloids on the non-metal side will have non-metal characteristics. So we're going over here to group 15. Everything will have a -3 charge up to the line, up to this staircase. Okay? You can say, well, what about antimony and bismuth? All right, if you remember back, antimony and bismuth are called post-transition metals, and they can change charge. All right. Over here in group 14, which is the carbon group. All right, carbon and silicon are -4. All right, anything below here, germanium, tin, and lead, they can change charge. Again, they will be positive since they have metals. They're metals and they have metallic characteristics. So again, carbon, silicon, -4 up to this line. Boron tends to form a -3 charge. Again, up to the line. So there's only one element in group 13 that can form a +3 charge, sorry, a -3 charge. Aluminum and gallium will also have a set charge of +3. All right, so aluminum and gallium are always +3 all the time. Indium and thallium, though, they can transition because they are post-transition metals, and we'll talk about a little bit more of that in a second. With this information, you can look at an element. So if I ask you, well, what's the charge of phosphorus when it gets one, you could say it has a -3 charge. Okay. Now, elements, when they're by themselves, don't have a charge. Usually when they form a compound, especially an ionic one, they will get a charge. Okay. So we're talking about the charges that they can obtain if they do get one. All right. But elements are mostly neutral. Okay. But they can get a charge. So we're going to talk about group 3 to 12 over here. Again, we call those transition metals or transition elements. Okay, they require Roman numerals, and I gave you 3 exceptions, and you need to know them. Silver is one of them. Silver doesn't transition, it always has a +1 charge. Zinc and cadmium are also 2 exceptions. Zinc has a 2+ charge, and cadmium has a 3+ charge. All right, but everything else in group 3 to 12 can transition. All right, so again, nickel could be usually +1, +2, +3. All right, and again, the way I indicate that is through the use of Roman numerals. Now, don't worry about the elements all the way down here, all this UU stuff. All right, we're not going to deal with anything like that. We're not going to deal with compounds of the lanthanide and actinide series just yet, but they do get charges similar to that of the transition metals, where they can change charge. So, but we're not going to worry about that too much for right now. All right. So, again, the transition metals need Roman numerals. Going back to these elements right here: germanium, tin, indium, thallium, lead, bismuth, and antimony. Those 7 right there are called post-transition metals. They need Roman numerals as well. So if I was to write out something like a compound like lead iodide, okay, which sometimes could be either +2 or 4, I would have to put, if it was lead 2 iodide, I'd have to put those Roman numerals in too. And we're going to teach you how to do that. But for right now, you just need to know that these elements have to have Roman numerals on them when they're written out. Okay. Again, to reiterate, most everything are metals. You got the alkali metals here, the alkaline earth metals here, the transition metals, the post-transition metals. All right, aluminum is a metal even though it's on the metalloid line. And here we have the nonmetals. Okay, so this stuff is super, super, super important. You will not be able to get through the rest of the course without having mastered this material. All right, this stuff is not going away. All right, and we need to have this locked down and mastered very, very soon before we go on. So basically every concept we're going to work on, not all of them, but just about every one of them, are going to be based upon the fact that you know where things are on the periodic table, if they're metals, if they're non-metals, what their charges could possibly be if they get a charge, okay, and as well as their blocks. Okay, and that ends this video. Thank you for watching.